Okay, let's see where we have stopped last time. Okay, so this chapter quite chill one. It's mainly about heat and temperature. And why is my one not frozen? Triple Mate, you okay? Yeah, show this one first. Hmm. Okay, so the last place we stopped is we looked at both the different states of a substance, the solid, liquid, and gas. And we know that basic things like the shape and the volume, okay? But what we need to now look at is if when we change the state from solid to liquid to gas, we need to add heat to the system. And we all know this now, we heat up ice, become liquid, we heat up liquid, become gas, okay? So when we say we add heat, so if you look at this point here, it's like, oh, heat is added. So this so-called heat is added. Today, we're going to look at how to calculate the amount of heat needed to change the temperature of an object and then to change the state of an object. Okay, because when we add heat to the system, the energy increase, all right? So the potential energy will increase when you go from solid to liquid to gas. Your kinetic energy will increase when you go from solid to liquid to gas. So all this increase in energy, by conservation of energy, the energy have to come from somewhere. So it comes from the heating that you are giving to the system, right? Last week, we basically looked at the type of thermometers. Okay, we looked at how to measure temperature, mainly using the Celsius scale. And when we measure temperature, we focus a lot on the fixed point, which basically is using ratio. Okay, so our fixed point is we use 0 degrees Celsius as melting point and 100 degrees Celsius as boiling point. Okay, and mainly we looked at the different type of thermometer lah, okay, and how it works. This is not very popular. We'll do more questions. Okay, so today we're gonna maybe and probably look at of and also case of heat transfer, which is conduction, convection, and radiation. Also learned before in general science. Okay, so now we're going to look at heat transfer. So just let me adjust the notes a bit. All right, so we looked at temperature, and fast forward for this. No, we'll come back to this later. I want to do some calculation today. This one. So let me throw this into the Discord. Calculating the amount of heat transfer. If got lag, like very bad lag, you let me know, okay? I can feel the internet struggling. If it's very bad, I will disconnect and use my laptop's mic. Sound would be a bit weird, but it's okay, better than lag. Actually, at this point in time in my life, everything is better than lag. Let me paste this page into your one. Into your Discord. These are all from your textbook. When you scroll to 5.10, it will be there. Right now, I'm just waiting for load. Okay. Okay, while the page loads, which is going to take a few minutes, we can start first. All right. So whenever we heat something, okay, let's say for example, I heat up some water, okay, I need to send it some thermal energy, which is another way of looking at heat. Okay, no need to write notes first, later I'll write on top for you. Okay, so let's say for example, we compare two substances, all right, let's say we have 1 kg of water and 1 kg of aluminium, okay, and I want to increase the temperature by 1 degree Celsius. So what I'm doing here is now I add heat to 1 kg of water, and then the increase in temperature is 1 degree Celsius. So for water, I actually need more heat. And the reason why I need more heat is because water is actually a pretty good insulator. All right. So if you, let's say after a hot day, like today quite hot, let me look outside. Oh yeah, today quite hot. Okay. So if after today and your condo got swimming pool, and you go into the swimming pool after dinner, you will notice that the pool is still hot because the water still retains some of that heat inside itself. And when you jump into the pool, you will feel that amount of heat. Okay. So finally, the page has loaded. So I'm just going to throw this into this. All right. Okay. So let's compare this to aluminium. And we all know aluminium is not a really good heat conductor. I mean, sorry, it's a very good heat conductor. It doesn't store heat, doesn't hold on to heat well. So if this number is big, this means that the substance here is water, needs a lot of heat, or rather needs more heat. All right. So we compare this to aluminium, which is generally a good conductor. So the reverse will happen. Aluminium only needs 900 joule, which is 4 times less. Okay, for 1 kilogram of aluminium to increase its temperature by 1 degree Celsius. So scientifically speaking, we can then say that water has a specific heat capacity of 4200 joule for every kg for every degree Celsius. Joule per kg per degree Celsius. And aluminium, being a metal, has a specific heat capacity of 900 joule per kg per degree Celsius. All right. So if I want to write this down as a general equation, okay, I'm going to move up there and then maybe I'll write it here and then I'll write it in the notes. So the third theme that we're looking at is specific heating of an object. So I'll just talk about this one. I'll pull it up to the mind map later. Heating of a substance. So let's say I have a substance here, okay, and I add some heat added, let's say Q. Symbol I will use is Q. Unit here would be joule. Okay. And let's say this is a substance of mass M. So this substance is mass M. All right. So then I add this amount of heat and I notice that the temperature increases or raises by T. So I'm going to draw a thermometer here. So the temperature increase by T. So the physical quantity we're dealing with is heat energy or thermal energy that I've added to a particular mass, and then I look at the increase in temperature. So the understanding of specific heat capacity, you see the word C here, C for capacity. So C would be the amount of heat required per unit mass per kilogram per degree Celsius or per temperature. So I'm going to write this one as T. Okay. Which is also something like 402,000 joule per 1 kg per 1 degree Celsius. This one is for water. Okay, so in normal talk, let's say I have iced coffee, right? And I want the iced coffee to be hot because I like hot coffee. So how much heat do I need to add into this coffee so that the temperature increase by 20 degrees Celsius? So I take 4200 multiply by 20, and maybe this is just 500 grams, so multiply by 0.5. So this number allows us, this number allows us to actually make a basis of comparison. Or if let's say you don't like this, maybe I'm going to define the C first. So this C is defined as the amount of thermal energy or amount of heat required per unit mass divided by M per unit increase in temperature. Okay, so amount of heat required, that would be this one, this Q here, heating up. Okay, per unit mass would be the divide by M. This is per unit mass. Okay, per unit increase in temperature, this is T. The word increase is compulsory, okay? Because the whole point here is I add heat to something and then let something have a change in temperature. If there's no change in temperature, then nothing is happening. Okay. So as usual, students don't like equation with fractions. So we rearrange, okay? We throw the M and T on the other side. I get Q is equal to MCT. Okay. And because I have a potato brain, I want to make sure that I remember that I need to like increase in temperature. So I need to take final temperature minus initial temperature. So I'm going to put the triangle here, delta, to show the change. Because why? I forget to minus initial and final. So I better include this inside my equation. Okay. So in other words, now what we have is heat or thermal energy. I want to use this equation. This is the mass of the substance, and this T would be your change in temperature. Of course, the reverse process can happen. You can remove heat, but we're going to use the same calculation. It's just that now instead of adding heat, I take away the heat. Okay, and very important, sometimes they will ask you to define what specific heat capacity C is. Okay, so please know what specific, how to define it or write it in a sentence. It's basically the same equation. Alright， 你只是把那个 M 跟 T 移去那边，然后你就 heat per unit mass per unit increase in temperature. Alright, SPM definition a bit different. So if you do the SPM one, follow the SPM style, okay? Anyway, we're gonna try some questions now. And I will screenshot this. Scott, give me a minute. Then I'll throw it on top later, okay? Okay. Loaded. Okay. Let's look at some of our hangout. You can choose a question to do. Theme. Maybe we will look at Okay. Since it's hot, we're going to take a shower. Let's look at the shower question. Okay, so this one is just very blur. Let me see if you can see this question. Screenshot. Okay lah, 勉强 okay. Okay, so this one was given on the 9th of July. But in case you don't know where to find it, So I already opened the whole thing. Crop and put inside. Okay, let's go. So figure 6.1 shows a shower that takes in cold water and the water passes through an electric water heater. So I think all of us have this in our house, right? Unless your house is very changgeh one, the whole house hot water. Wow, your house, huh? Okay, like my house only got hot water and the shower, okay? And if I turn it on, and if the pump is working and the water pressure is enough. Okay, anyway, so this is the electric water heater, okay? And it says that the power of the heater is 900 watt. So I'm going to do this exercise where I will write out other equations that is maybe needed in relating to this kind of heating question. Like for example, in this question, we are about to heat water, right? So power, if you remember, is energy over time, right? And this energy can be any energy. The important thing here is that this is the energy that changes over time. So currently, this is obviously heat energy lah. Okay, there's no kinetic energy, nothing, just heat into the water. All right. So that means the power. This means that the heater is able to provide water 9,000 joule every second. 900 joule, 9,000 joule of heat every second. Looks like a lot, right? 9,000 joule of heat every second. Okay, so part A, A1 is sort of like using equation from, from your younger years, if you remember. But if you don't, we will cover them again in year 11. It says here that the shower is powered by a 230 volt electric supply. So the switch that you turn on to start your water heater, it provides this much energy. Okay, calculate the current. All right, so power is energy over time, but power is also equal to VI, or in other case, voltage multiplied by current. VI, victory, a lot of current, V. Anyway, this is 230, this is 9,000, I, and we can calculate I. 39 Gg.1 ampere. Good. Let me see if I will press wrongly. Oh no, okay. It's a bit high lah, which sort of makes sense because every time if there's an accident, people get electrocuted is normally when they're taking a shower. I think a few months ago there was an accident in Cameron Highlands, which is very similar. So you want to avoid being electrocuted. Most of the time, there's safety in place in the electrical heater. And for example, there could be a fuse in the heater circuit. So what a fuse is this thing, that is connected to your circuit. Now inside the fuse, try to draw a fuse, there's this tiny wire. Okay, and the fuse here got rating 1. So obviously I'm going to at least use a 40 ampere rating. 40 ampere rating fuse. Okay, maybe I want to use 40. Okay. Why? Because any current more than 40, the wire will burn and then it will break. And any current more than 40 ampere, this thing will break, will burn and break. So the fuse short circuit. Fuse burns, break. So 40 is good. You also don't want it to be 39. If not, then every time you take a shower, you have to replace the fuse and that will be a bit annoying. So you have to open the shower and no. We don't want that. Okay. All right. So right now we continue the question first. heat capacity of water, 4200 joule per kg per degree Celsius. You don't need to remember the 4200. They have to give you in the exam, okay? Because these are just facts, right? Initial temperature of the cold water is 16 degrees Celsius, okay? So initial temperature, maybe I'll call this T1. Determine the maximum mass of water that can be heated. So I want to find M. That can be heated to 35 degrees Celsius, T2, in 1 second. Okay, so I know the equation. Q is equal to mc delta T. You could also write, you can also look at this one. You see, bring here. Joule per kg per degree Celsius. So what is, sorry, joule per kg per degree Celsius? This is your specific heat capacity, right? So this one would be Q over M delta theta. So you bring this one up, Q will be equal to M 4200 delta theta. So you can always use the unit to help you sort of remember the equation. Really, you can see, I write them side by side, but the blue one you're going to write also can. All right, so you can write 4200 is Q over M delta theta. I prefer to write this way because it's linear, takes up less space in my question paper. Oh wait, you come from Catholic High. You know how small your question paper can be. No space. Okay, anyway, how much heat do I have? So I also remember, I'm going to write down the equations that I will use at the side, that power is actually heat energy over time. So heat energy is power multiplied by time. And this will be mc delta T. Okay, stop me anytime if you need me to, if I'm going too fast. All right. So you want to find the amount of heat is P times T. Okay. I think we have enough information. We can substitute now. Heater is 9,000 watt per second, and they say 1 second. T is 1 second. Okay. So yeah, times 1. We're looking for how much mass we can possibly heat. 4200. I guess I'll write this in green for you. This is 4200, the specific heat capacity. And the change in temperature that we have is 35 minus 16. Okay, I can find M already. Oops. So 9,000 divided by 4200. 35 minus 16. Okay, so 0.113 kg. What do you think about this water heater?
No comment,
Yes.
TBH.
Sorry?
No comment, TBH.
No comment. So 1 second, you only get like 100 grams of water. That's like 100 milliliter. So 1 second, your shower can only heat up like this much water. Not enough. The comment is not enough. I need a more powerful one. Anyway, that's fine. Teacher, why is this 4 marks? I go look at the mark scheme now. Okay, so apparently, if you use energy is power times time, or power is energy, basically you got write this one. You get 1 mark already. Very nice, Gonna bracket. Doesn't make my working looks nice. Okay, so this part here is 1 mark. Calculation 1. You have Q is equal to mc delta theta. You get another 1 mark. And then you substitute everything correctly, 1 mark. Final answer, 1 mark. Very good. Bonus, 4 marks. Okay. That too is pretty straightforward, like just 1 mark each. This one is 1 mark, A1. And this one, if you write the equation, is 1 mark. The final answer, substitution and final answer is the other mark. If you care about where the mark is, if not, you just do. I think this is not enough water for 1 second. Or I guess maybe enough. Who knows? Okay. Just make sure the answer is not like very weird, like either too big, 13 kg, means you didn't convert something, all right, or too small. Okay, let's look at the last part of the question first. Oh, finish. No, it's this side. Okay, next side. Okay. A safety control in the shower switches off when the water becomes dangerously hot. Have you ever been to like a hotel and then you don't know how to use the shower, then you accidentally burn yourself? Okay, this control uses a thermocouple thermometer to measure the temperature of the heated water. I guess that makes sense because you want to make sure that you want to turn it off fast, right? So it has a fast response time. So part 2 suggests one reason why we choose a thermocouple, fast response time. So the thermometer, I answer this one first. The thermocouple thermometer. Thermocouple thermometer response quickly to change in temperature. Right, so that you can turn off the power supply before the person get real injury. Okay, so how do you draw a diagram or describe the structure? So maybe I describe the structure first, okay? So then only maybe I draw. But the whole idea of a thermocouple, if you want to look at it, we have looked at one last week somewhere. Last week. Yes, here. And that one. Okay. So what we need is, number 1, we need 2 wire and we need a voltmeter. Okay. And number 2, what we need is we need to put the water at 2 different ends, different water at different temperature. So essentially what we need to do is we need to copy this diagram. Okay. So I will do so now. Okay. This is another thermometer, all right? Thermometer that can help you turn off when the temperature is too hot. So we have 2 different temperature to be measured, and we have 2 different metals. So you're gonna have a voltmeter, maybe something like this. Okay. So you could say this one is metal A. You don't need to know the type of metal because you're not studying chemistry yet. Or rather, this is not a chemistry class. Got metal A and metal B. Like this. Have a voltmeter in between. And then this part here is the cold water. What's the cold water again? At 16 degrees Celsius. And this one here is the hot water at 35 degrees Celsius. Okay. So if the voltmeter reading increases, or the voltmeter reading increases as the temperature difference increases. So currently we want a temperature difference of 19, is it 19? Yeah, 19 degrees Celsius. Yeah, 19, okay. So if the temperature difference is more, then the voltmeter reading increases. This can trigger the off switch. So what I need to do is I just need to connect the voltmeter into another circuit to turn off the heater. So the second good thing about a thermocouple thermometer is that it also provides an electrical output if the voltmeter reading is too large. Okay, so triggering the off switch or turning off the water heater. So the way it works is like this. Let's say I have this voltmeter already connected to my shower, and every day I take a shower, and let's say for temperature difference of 16 degree heat to 35 degree, my voltmeter reading, example, I don't know what's the voltmeter reading, I have 1 volt. So every day I take a shower, every day the voltmeter is 1 volt, every day is fine. One fine day, I turn on the shower, and then for some reason, I don't know why, my heater go haywire and bring this up to 50 degrees. So maybe now my voltmeter reading is 2 volts. Example, okay? So what will happen is that the voltmeter is like, oh, GG, every day 1, why suddenly 2, 1, then trigger the off switch. But how does a voltmeter talk to the off switch? You need another circuit to connect to the off switch, is power supply. We'll study more about this in year 11, but the whole idea is that circuits can talk to each other. So if I have electrical output, I can trigger the off switch. If not, then, or maybe the alarm will, I don't know, but the alarm doesn't help, so it's off. Okay. Let's use. So now we're gonna go back to the notes and fill in the extra power equations that we have used. Okay. So power is Q over T. So heat is power times time. This can be helpful. And also, number 2, power is voltage times current. P is VR. So heat is power times time. Power is voltage times current. Wait a minute. If I combine these two, I will also get Q is equal to VIP. Okay, ma? Because this P, I sub inside. So in place of P, I put VI and I give VIT. So sometimes they'll give you the power rating of the heater. And you're like, okay, I'll just multiply by time. But sometimes they will say, oh, 2 ampere of current is passed through a heater of a 10 volt. Okay, sure, you take 2 times 10. Okay, everything today is multiplied. All the equation multiply one. All right, let's look at some experiments now. Okay, that was a real life application. And I just want to show you some specific heat capacity of different things in this world. So different substance will have different specific heat capacity. let's say you compare between water, alcohol, ice, copper. Generally speaking, the lower the specific heat capacity, low C means better conductor, better heat conductor. You look at the substance, you know already. No? These are all metal, and then up here is just insulator. Yeah, I guess I'll just write here now for you. So another thing to know, so I guess maybe I'll call this A, specific heat capacity. Okay, and also next one would be lower C, better conductor of heat. The temperature will increase very fast and it will just pass on the temperature, the heat. Okay. So you don't need to know the number they will give you in the exam, but you have to know that if let's say I say copper is 400, but water is 4,200, which one is a better heat conductor and why? So you can use specific heat capacity as an explanation. By the way, if you go and eat like Indian food, you notice that generally their cups are made out of like metal. This is the reason, so that their teh tarik will cool down faster. A glass, they're not really. Okay, so right now you may be wondering, so how did the scientists get all these numbers? They do experiment, right? So this is an example of the experiment, and later we'll do a question involving this. But what we have right now in this experiment is we have a heater. You can see that this one is the heater, right? It's the electric heater. You connect to the power supply like that. Okay. And then inside this heater, I submerge it inside maybe a beaker that I can put any of my substance. So I can pour water, I can pour alcohol. If I want to use a solid block of ice, I can. I just drill a hole. I drill a hole here, and stick the heater inside. Okay. And then there is a thermometer, obviously, to measure the change in temperature. And to make sure that the heat doesn't go to the surrounding, I tap out the whole thing inside insulator, like maybe polystyrene or cotton or wool. Okay, so I basically just wait for a given period of time, because to find Q, here I can use VIT. So in this power supply, I will connect this to battery, because battery will give me current, right? And to measure the amount of current, I will put an ammeter in series with the battery. Okay, teacher, the voltage, you can read the power rating, or maybe you connect a voltmeter like that. It's a different color. We'll connect a voltmeter. I'll draw another one for you later. Okay, so we're going to use this system, and we'll use Q is equal to VIT, can read from the meter and then multiply by time. So let's say I let the experiment run for like 5 minutes. And in that 5 minutes, I measure my delta T from the thermometer. So from here, I can then combine these two equations into C is equal to Q over M delta T. Delta T can sub inside here. Q can sub inside here. And obviously, I know how to measure the mass of the water that I put inside. Ring machine, ring balance, or mass of the substance that I put inside. So mass is never a problem. So I can put everything inside and I can calculate my C. So this M is measured using a balance scale. So generally, this is how the experiment works. We have a device where we stick the heater in and pour our substance inside. Or if it's a solid format, then we put the solid inside and then we drill a hole to put the heater inside. This is immersion heater. I'll call it a sous vide. If you use this at home in the kitchen, apparently people use it to cook steak. Okay. All right, let's try a question involving this. Reason one.
Teacher,
Okay. Yes.
85D.
85 ah. 85 ah. You fly very far. Okay lah, we do 85. But this one cannot yet because this one has boiling. So there's a change in state. We haven't reached there yet. So far we heat stuff only. We never changed the state yet. So we're going to look at probably this one. 80. Okay. So this is an example of the same setup. The only difference is that this one look a bit low tech because I'm heating sand. Interesting. So this side here is all sand. I put a thermometer inside there. And I'm hoping that the plastic cup is a good enough insulator. But we'll see. The power of the heater is 50 watts. Okay. And the mass of the sand in the cup is 550 grams. The initial temperature is 20 degrees Celsius. So this is T1. And the heater is switched on for 2 minutes. Turn on the heater for 2 minutes. The temperature is recorded until the temperature stops increasing. Okay, sure. The highest temperature recorded in these 2 minutes is 33 degrees Celsius. T2. Okay, so you may be thinking, why want to record until the temperature stop increasing? Well, if you cook food, I don't know if you do, there's this idea called carryover heat. So for example, you turn off the heater, there is still heat that is slowly moving into the sand and the thermometer. So you need to wait for that to happen. But either way, you just measure the largest temperature. Okay, calculate the energy supplied to the heater, Q. Part 1. And number 2, calculate a value of specific heat capacity C using the answer and also the data in the question. Okay, maybe I'll give you 5 minutes to do this. It's very similar to the one that we did just now, but the only difference is they gave you a lot of they step 1, step 2 lah, instead of putting all together in 4 marks. Okay, try now. If you want the question, soft copy of the question, I'll throw it into. Yeah, smart this to the side.
Teacher, is the minutes in second or what?
Is the minutes in second or what?
I mean, is the time, is the T in, well, I want to find Q equals to PT, so the T that I know, should it be in second or minutes?
Everything should be in SI. Standard units. So it should be in seconds.
So it should be in seconds. Can I just, so Q equals to PT is already the answer, so I don't need to go Q equals to MC, change in T lah. Okay, never mind.
You also kind of don't know what C is, right? In fact, part 2 asks you to find C. Anyway, the question is also in Discord if you need it. Okay.
Mass in kg hor.
Everything now SI. Okay, let's check answer. So as previously pointed out, the energy, you can use power multiplied by time. So 50-watt tiny heater, 2 minutes, 60 seconds for each minute. So this will be, I guess, 6,000 joule. 100 times 60. Yes. 6,000 joules. Don't forget your unit, okay? Calculate a value for your specific heat capacity. So it's either you know that C is equal to Q over M theta or MT, or I guess you could just go with Q is equal to MC change in temperature, and 6,000 is your mass, which is 550. So need to convert to kg, so 0.550, okay? C, and the change in temperature was 33 minus 20. So this means our C here would be 6,000 divided by 0.55 divided by 33 minus 20. So 839 joule per kilogram, because I divided by 0.55 per degree Celsius, because I multiply by the change in temperature. I mean, you don't want to write power -1. You can also write 839 joule per kg degree Celsius. Also can like this. So this means I need 839 joule, but if I want to increase the temperature of 1 kg of sand by 1 degree Celsius. Sand is not a very good insulator. Or very okay, 800, neither here nor there. All right, explain why the specific heat capacity of sand may be different. Okay, what is a bit sus about this experiment? Hint, something they forgot to do. What do you think that is? I show you here. Something is missing. I draw. Something is missing here. What should I put here? What should I put here? What is missing here?
Something.
Because would the heater accidentally heat the air around it? Could be, right? And maybe the sand is hot and then it will also heat the air around it. Yeah, so basically heat will escape. I should have tapao this whole thing in the insulator. It's like you buy frozen fish from the supermarket. You want to wrap the fish in newspaper, you don't just want to wrap in insulator, no insulator. Okay? So because there's no insulator, so number one, there could be heat loss to surrounding. So some of the thermal energy from the heater has escaped, is lost to surrounding. So if let's say I take all the energy that is lost to surrounding, I rewind and put it back inside the sand, the temperature increase of the sand should be bigger, right? Does that make sense? So for example, we have Q is equal to MC delta T. Okay, so this 600, this 6,000 is fixed one. I thought all of this 6,000 has went to my sand, but actually no. Maybe 600 is lost to surrounding. So if that's the case, then this 600 loss, I put it back inside the sand. Maybe instead of 33, my temperature will increase to, I don't know, 35. You understand? Because some of the energy lost already, to surrounding. So supposed to be hotter one, but some of the heating has lost. So if I expect it's supposed to have a larger change in temperature. Then if I repeat this calculation, that's why it's if no heat lost, maybe the final temperature will be greater than 35. 33 degrees Celsius. So let's say 35. We just put a number there to help our brain think. So if you repeat this calculation, whatever you calculate, this C will be less than 839. Because now you are dividing by, previously 33 minus 20 is 13. Now 35 minus 20 is 15. So you are dividing a larger number to find C. So the C is less. So because they say, explain why the specific heat capacity of sun may be different from the value. So how is it different? You can say that the specific heat capacity, hence the specific heat capacity is less than 839 joule per kg per degree Celsius. Or less than the value in part 2 also can. So you thought you need 839 joule for every kg, but actually you don't need one. You need less than that. You need so much is because you always say low. So, okay. Yes. This is the unfortunate thing about surrounding. You generally need more than, there's always loss. You thought you do 2 examples, students understand this, but actually they forget one of the example because their brain zone out. Okay. So the student capacity is actually less than what the teacher estimates. And the teacher, or especially the older teacher, or it's my teacher, will nag me, teach how many times already, still don't know. And then I noticed that, well, the second half of the class, my brain is in la la land. So of course, I don't know, I wasn't paying attention. The counter to that is, notice when your brain is in la la land, it's tired, cannot pay attention, it's okay. You just go back, you open another 10, 15 minutes, look at it, probably you'll be fine if you don't zone out too much. Yeah, but 2022 got recording. During my time, where got recording, also sit there and brain dead, brain dead. Well, okay. Anyway, that was a tangent. The whole idea here is surrounding will affect your experiment. The best thing to do is to insulate the thing. Okay. So now we're going to look at something that's related to the question that you already mentioned just now. But where did I come here? It should be here. Okay. So I just want to point out that this measurement of specific heat capacity, okay, this whole thing, is useful when we want to heat up an object and change the temperature. But sometimes we heat up the object because we want to change the state. So maybe I want to boil water to cook Maggi mee. I want it to be a rolling boil. Maybe I want to melt ice. So when the state change comes in, something slightly different will happen. So let us look at that. All right. So whenever there's a state change, we use the term latent heat. Okay. So in English, latent here means no change. Latent. So whenever you see latent, it's like, oh, something is like not motivated to change. Just, you know what? 2020. Let's see Google. No, I can hear your school got people cheering outside. So happening. Okay. Latent. Lying dormant or hidden. No change. Not yet changed. Not yet developed. Hidden or concealed. Wow, this is the English lesson of the day. So when we say something is latent, no change, or rather the reason why we say no change is no change in temperature. And we often measure heat by using temperature, right? So if there's no change in temperature, it's as if there is hidden heat, question mark. So recently in my college, I just marked a bunch of A-level students' answer. And then asked them, like, is there heat needed when boiling water? And then a lot of them, they say, well, no change in temperature when boiling water. So no heat needed. Lor. And then I just sit there and I'm like, this one don't understand. What is latent? So latent means no change in temperature or the heat is hidden. 你量不到那个 temperature increase, 你就以为它没有 heat 吗？因为 heat 是 Q is mc delta theta. So no change in temperature delta theta 0. Does it mean that heat is 0? Anybody with logic brain know it's not the case, right? Because you want to boil something, obviously we need heat, teacher, we need a lot of heat, all right? Okay, so that's why we look at this thing called latent heat. And if you look at the heating curve, okay, of this temperature, you notice that something will go from, let's say, solid, -20, here to here. What is going on from here to here is mc delta T. This is not latent heat. I'm heating up the ice from -20 to 0. So 0 minus -20. If you want to be like very particular about how you write, or you can just write 20 degrees. Okay. So here is mc delta T. And in fact, I can sub the value in if I know the specific heat of ice. Okay. And then liquid here, you can see the temperature also increase. So here to here is also mc delta T. So whenever there is a climb in temperature, we can use mc delta T. We know that there is heat. But now the question is, from here to here, how to measure heat? Because if I say there's no heat, you're like, teacher, cannot be lah, right? You want to melt ice, have to have heat. Well, that's true. And the reason why you don't see the temperature increase is because when we are melting, we are increasing the the molecule separation. So when we increase and we break the bonds, the heat is used to break bonds. So then the temperature cannot increase now. Because your heat can only do one thing. Your heat can either increase your temperature or break bond. Which one you want? You want to break the bond? You want to change from solid to liquid? Okay, temperature cannot increase that. Okay, that's why we call it latent. So this latent and got two different state change. The first one is latent heat of fusion. Fuse here is something changing state from solid to liquid or liquid to solid, depending on whether you add heat or you remove heat. Okay, so this one requires a lot of energy. It's not like 4,200. You look at this 330,000, a lot more zeros. Why? Because this is the energy needed to separate the particles so that they can form the liquid. It's like I need to stretch out all the particles so that they are now in liquid form. It's a lot of energy, man. Okay, so it's called latent heat of fusion. Because the temperature doesn't change, it simply means how much heat do I need to change 1 kg of this substance from solid to liquid. 1 kg. Okay, so you can always generally see this as, in solids, the particles are held together by strong attraction. So we're just going to stretch them, and that needs us to add energy. Okay, so I'm going to just write this at the side later. And if you want to measure specific latent heat, okay, the same thing is the case. We are going to put ice inside a funnel like that. Probably do a question later. And then we stick the heater. And what the heater does is melt ice, and we can measure how much ice is being melted by measuring the weight. All right, that will be the latent heat of fusion. So I'm going to write all of this to the side. we will draw the experimental setup a bit later. But for B, we're going to look at specific latent heat. Symbol is L. Okay, so meaning now I want to take 1 kg of ice or 1 kg of substance, still 1 kg. And I want to add heat so that this 1 kg will become 1 kg of powder. Can I? It may not be one line, it can be any amount of energy. Okay, so which means this L, right, can be defined as the amount of heat required per unit mass, joule per kg. So we define L as the amount of heat per unit mass required to change solid to liquid at constant temperature. Well, at the end of the day, you and I prefer a linear equation. So we're still going to stick with this. Okay, just that our main character here is not our L. It's an easier one because the temperature doesn't change. Which means if I look at my heating curve, I'm going to draw one here. This is temperature. This is time, maybe in seconds. Temperature in degrees Celsius. Let's say I start with -10. Okay, so heat. Actually, hang on. Heat. Melt. And then we will heat again. Wait a minute. Somewhere here, another state change will happen, right? At 100 degrees Celsius. So this part here, if you want to calculate the heat, you will use ml. But this is latent heat of fusion. Maybe I put a tiny f here to show us that it is latent heat of fusion. LF. And you don't want to put also L-. Then you can see what is going to happen later, right? Somewhere here, there's another state change. Okay. And at this part here, I will call this the latent heat of vaporization, because we are converting from a liquid to gas. Melting, boiling. Here to here, MC delta T. But the delta T is 100 degrees Celsius. Okay. Here to here. Also, MC delta T. But this one is for ice lah. Okay. And this one is for water. From here to here. So you just have to ask yourself, in the process that I see in the question, is the thing melting? Is the thing boiling? Or is the thing only changing temperature? So it should be pretty obvious the way they present itself in the question, okay? So just to top up the last part of our notes, I guess now since I separate fusion, should probably also define the second specific heat, specific latent heat of vaporization. LV. Still Q over M. Same equation, bro. The only difference is the state change. So you can copy everything. It's just that now we are changing from solid to liquid to gas. Okay. Let me pull this down. Okay, it's good enough. Draw a line. So you want to define LV? LV is not the bag. We're going to go from, okay, by the way, this one, if it's ice, is 0 degrees Celsius ice to 0 degrees Celsius water. Only for state change. So legit, just, just from here to here only. If my ice not yet 0 degrees Celsius, I need to add more heat until 0. Okay. So like, for example, this one would be 100 degrees Celsius liquid. We'll change this to 100 degrees Celsius steam. And after that, 你要继续 become hotter, you continue lah, okay? Not by business, just continue. Just continue only. Okay? So you find this boiling. This is 100 degrees Celsius. So 1 kg water, 1 kg steam. Lemao. So this LV here is the amount of heat per unit mass required to change liquid to gas at constant temperature. Will the values be different? Yes. You need more energy to boil water compared to melting ice per kg. Makes sense, right? Water, you just separate a bit only. Solid to water, you separate a bit. Water to steam, you just have to push the particles very far apart. That needs a lot of energy. And you need to push against atmosphere, that needs more energy. Thank you, Mr. Kong. Should I go to 3.6 liter? Someone was there just now. Yeah. Okay. So next week we will continue and we'll do more questions involving this, but let me assign some homework first. Okay. So make sure you practice. So today what we've covered is what happens when we heat MC delta T, the first set of equations, and then what happens when we melt Q is equal to ml or boil. Okay. The important thing to know is that this Q can be calculated using PT, green equation on the left, or P can be calculated using VR. Because normally when we heat stuff, we use electricity. Okay. And finally, just a reminder, different parts of the heating process will use different equation. So you have to read at which point do I start heating. Like the sand, there is no state change. Okay. Sand is not going to melt into liquid sand. So you are set. But if it's ice or if it's another substance, then please read the question. All right. I will screenshot this and throw in the chat later. So you don't need to rush yourself, but let me assign some homework. So you should do So you can do 62 Yes, do 62. 62, 63. I want to say do 65, but I guess you have to wait. 62, 63, 64, 69, 71.
Yeah, that's about.
That's a lot. A lot. 77. We choose first. Then we will cut from there. Okay lah, your favorite lah, 85. Okay. I'll type in the chat and then I'll put bracket around those that is not compulsory. I'll choose 3. Okay, Yurui, is 3 enough?
Okay.
Okay, 3 lah, 3. I'll type all that is related to today if you need extra practice. If you want to do more than that, then it's up to you, but I'll choose 3. Okay, thank you, Jeremy, Yurui, and Charlene. I'll see you. Stay hot. Go heat yourself. Okay, I need to change class. Bye-bye.